Thank you very much, Ricardo. Thank you, Mr. Chairman. Ladies and gentlemen, good afternoon. I can't tell you how nice it is to switch from organizer to speaker and do some serious research stuff, I hope. So as I announced during the first day, I will give you an overview of the numerical tools we are developing for superfluids in our group at the University of Rouen, Normandy. And if you ask where is Rouen, it's not very far from Paris, 150 kilometers northwest, near the D-Day beaches, completely different style of beaches in Normandy. And it's a very nice city, historical. See how proud is the cathedral. And here you have a picture of the cathedral meshed with FreeFAM++, the software I will present to you today. At the LMRS, it's a math laboratory, and I'm a professor in applied mathematics. So my main job is to do numerical analysis and scientific computing at the interface with other disciplines, like physics, fluid mechanics. So one of the topics we're dealing with is solving Navier-Stokes equations, in particular vortical structures. And recently we published with colleagues from Brighton a book on vortex ring models where you can find how to deduce the famous Kelvin formula that Giorgio presented in his talk for the velocity of the vortex ring. We're also dealing with liquid-solid phase change systems. So we're solving Navier-Stokes with Boussinesq approximation for thermal effects. And here you have a simulation of the ice melting, a very timely, unfortunately, topic today. And also superfluids. And of course, today I will give you some details of the numerical work we're doing on superfluids, Bose-Einstein condensates, and also quantum turbulence in helium. We're not so many. So we are two permanent professors, myself and Frankie Ludens, associate professor. Frankie is in the audience here. And a research engineer who helped us for the codes. He is leaving now the laboratory, and we hope to hire a good engineer this year. Of course, these are the pictures when we were younger, so much younger than today. But we always like to put on our wave pages old pictures, just to forget that the time is irreversible. So I was telling about the ENER project sponsoring this school. I won't go back to this, too much advertising. So I will go directly to the main topic. So what you'll see will be numerics. Many of the talks were focusing on the physics of superfluids, quantum turbulence, but we're applied mathematicians, so our main interest is in developing interesting and new numerical tools to deal with these problems. And as I always say to my students, if you want to do good numerical simulation, you need at least two ingredients. The first one is good mathematics, and the second one, good physical intuition. When I teach in physics, it's vice versa. So you need good physics and some intuition of what is a Sobolev space. So I will start by saying a few words about this intuition of vortices in classical fluids and in superfluids to see the difference between them. And also I'll go through many numerical methods. Sometimes my presentation could be subliminal, so like commercials, but you'll have references and links to web pages where you can download papers and numerical codes if you are interested in our developments. So when you see vortices in classical fluids, as during weather forecast, hurricanes, water flows, volcanoes emitting vortex rings or trailing vortices behind aircrafts, you have an intuition of what's a vortex, because I have the intimate conviction that the human brain has already integrated some of the laws of the nature, in particular the laws of fluid mechanics, maybe not Navier-Stokes entirely, but the intuition of velocity, pressure, and vorticity is there in our brain. So when this afternoon you poured some milk in your coffee instead, or in your tea if you're British, you were not astonished to see that you had a vortex in your cup. When you go to superfluids, the intuition is more difficult because they are fluids without viscosity. So we don't experience every day fluids without viscosity. So if you imagine a laser spoon rotating a Bose-Einstein condensate, which is the case here, the rotation will be only local and starting from a critical rotation frequency. And the rotation of the system will manifest by the nucleation of the famous quantum vortices, which are the dark spots here, where these are zones without atoms, condensed atoms. So if I summarize, in classical fluids, we have an easy intuition of vortices, velocity, pressure, but the mathematical description of vortices, or what is called coherent structure, is still a matter of debate. We've seen the Q criterion, the lambda 2 criterion, and so many others, but there's not a general consensus on how to identify such vortices in classical fluids. While in superfluids, it's the inverse. We have a difficult intuition, but we have a very simple mathematical description. We have seen during this week different superfluid flows, and the most studied, of course, are the superfluid helium and Bose-Einstein condensate, and we had pictures of experiments showing vortices in these systems. So if we go back to the identification of the vortices, if it has been introduced, but I wanted to show you this picture of the simulation of a prolate condensate with a single vortex line inside. In the years 2000, there was a kind of competition between scientists, experimentalists, to generate a single vortex line in a BEC. And was much debate on what's the shape of this line. It is a straight vortex in the prolate condensate from the north to the south pole, or is bented. And mathematical and physical theory, and then, of course, numerics, show that the good shape of the vortex, it's a U. So by the Madelung transformation, you see that the vortex is a line along which there are no condensed atoms, and there's a rotation around this line. So numerically, you identify vortices by plotting isosurfaces of low density, so low square modulus of the psi, and also you have to look at the circulation around this line. And the features of the quantized vortex were presented, in particular, the divergence of the velocity at the center of the vortex. There are several ways to obtain vortices in BEC. The first one I showed is by putting the condensate into rotation. Then, by looking at the wake of an object moving in the condensate. Of course, the object is a laser beam. And also, since this is a system, a highly controllable system, the phase can be manufactured. So very exotic vortices could be engineered in the BEC, but this paper is just theoretical. Nobody obtained in BEC star type vortices. So my point here is that, as I say, there was a kind of a scientific race in BEC to obtain a single vortex line in a BEC. So colleagues from LKB in ENS in Paris, they obtained such vortices with a single line or very few lines in the BEC. So the challenge for helium would be to obtain a flow with a single vortex line or a single vortex ring. Just to study it would be nice for our theoretical development and numerical simulations. But of course, we've seen that is quite complicated. So going back to numerics, to identify vortices, we use isosurfaces of low density, like here. And you have here the skin of the condensate, since the wave function goes to 0 outside the trap, and also phase portraits. So phase discontinuities go from the holes here, which are vortices, to the border of the condensate. And this is different from helium. And here we have a giant vortex. I will show you more pictures about this giant vortex in BEC. And if you want to take a look, oops. If you want to take a look, if it's working, no, it's not working. Okay, doesn't matter.
It's on the left there. I think it's there.
Oh, it's going on.
Yeah, it was there.
So finish this. Yeah. Jeez. No, it's okay. Don't worry. Yeah. You want to do? I don't have the Pink Floyd music with what. Okay, let's go again. No, it's not working. Lecture. Now at the end. So if you, oh, here it is. So let's see. So it's an image of the inside of condensate with the phase discontinuities. So quite psychedelic. But please don't sleep. We have many other slides. Okay. Good. I have 90 slides, sorry, but okay. So speaking about turbulence, so the intuition also says that if you have many vortices, you'll get turbulent, which is a word we hear in airplanes. Even thought in America now, they don't say it's a zone of turbulence. They say there's a zone of rough air. So maybe they have another definition of turbulence in American airlines now, right, Charles? Okay. That depends which company, yeah, you take. So we use Navier-Stokes equation, and we solve these equations. We have numerical costs to do this. And some characteristics, since there's a not universal definition of turbulence, is that the vorticity, which is a quantity we're interested on, is random in space and time. There are fluctuations, and it's a continuous function, regular continuous functions. So turbulence scales will occupy all the space of scales of the flow. And the smallest scale is set by the viscosity. In superturbulence, so I prefer to use the name superturbulence for the GP turbulence because it's pure superfluid flow here. We use the Gross-Pitaevsky equation. The trapping potential is put here to show that the GP equation can be used to study turbulence in superfluid helium and also in Bose-Einstein condensate. And turbulence here, as we have seen, it's a vortex-tangle turbulence, so the interaction, complex interaction between many quantized vortices. And we've seen that there are yet many open questions. Everybody's looking for Kolmogorov laws about in these fields, and this is a very active research field. Turbulence in BEC, also, it's an interesting topic, very newer than the turbulence in helium, of course, and there are pros and cons to study turbulence in BEC. BEC, it's a pure fluid system, highly controllable, so we can control everything inside. Vortices are much larger than in helium. You see that it's something that could be interesting for experimental observations. And to obtain turbulence, we can use rotating or oscillating condensate. The cons will be that there are no quantitative measurements like the second sound in BEC. the pertinence of statistics when you look at a turbulent field with several vortices, 10, 20, 30 vortices, or 100 vortices maximum. And the influence of the thermal cloud is something that is actively studied today. So from a practical view, from a mathematician point of view, when I discussed with colleagues from LKB, they said, well, turbulence in BEC could be interesting, but is no of interest because the BEC is a highly controllable system that is supposed to be used to design, I don't know, GPS with infinite precision and so on, while looking to set up turbulence in a system that is not natural turbulent. In classical fluids, we study turbulence because turbulence is everywhere. But in BEC, turbulence is not a natural state of the condensate. Good. This was a philosophical remark. Of course, quantum turbulence in helium, as we've seen, the difficulty of this problem is to encompass a large range of scales, starting from the vortex core, 10 to the minus 10 angstrom, to the diameter of the container, which could be up to 1 meter. And we have already seen that there are different models studying turbulence in helium. The GP for temperature equal to 0, the two-fluid model, HVBK in particular, and at the other end, the Navier-Stokes. So, of course, nobody's talking about Navier-Stokes. So I'll give you some ideas of our numerical codes dealing especially with the GP equation, and then about the code we developed for HVBK model. Okay? So some numerical methods for the GP equation. So here we need to have some mathematical content. And this is the time-dependent GP equation with an extra term we have added because we spent a lot of time studying BEC in rotation, as I showed. The experiments in LKB used a rotating BEC to obtain vortices and then prove the superfluidity of the system. And of course, the other terms are similar to what you have seen in previous talks. We have the time-independent GP equation that is used to look at ground and metastable states obtained from the time-dependent with the ansatz here. And you have, as Union presented this morning, a nonlinear eigenvalue problem. We should say that generally we solve this equation with the constraint of the mass conservation for the time-independent GP, mass and energy conservation for the time-dependent GP. And these are very important characteristics that a numerical scheme has to satisfy, because otherwise numerical simulations are not accurate. Using ground or metastable states, we can use the BDG linearization of the GP equation to study stable or unstable modes for different states that are of interest for physics. So the idea for students is to take this form of the variation, small variation of the wave function, introduce into the time-dependent GP equation, and neglect high-order terms in order to end up with the linear equation that has to be solved accurately to observe the eigenvalues and eigenmodes of the Bogoliubov-de equations. So computation of stationary states, because I give you more details about our methods of computation of stationary states, are useful to set up initial condition for time-dependent simulations. So if you start with a configuration with vortices, first you have to perform this imaginary time simulation to have a stable or metastable state. These are states that are observed in experiments, because in BEC, by example, as you've seen, the pictures are taken after time of fly of the condensate, and what they observed is the integrated density along the direction of observation. So you see that at the very beginning you have a kind of spaghetti lattice of vortices. The contrast observed in experiments is not so nice. And then when the vortices align or polarize, you have this very nice constant that you observe in the published papers. So sometimes we observe the experiments provide this kind of pictures, and these are not yet fully converged states for the stationary BEC GP equation. So minimization of the GP energy will allow us to find this kind of states that are of interest for experiments and also for the BDG analysis. So there are two different methods to deal with this problem, either to propagate the Euler-Lagrange equation corresponding to finding critical points of this energy, and these are the methods called imaginary time propagation, and Yuyun presented some methods this morning, or the direct minimization of the energy. And what I'll show you some exotic mathematical methods which are called Sobolev gradients that we developed for this problem. So very roughly the idea of these Sobolev gradient methods. The most celebrated method to do with this problem is the normalized gradient flow we've seen this morning. So you take the Euler-Lagrange equation, which is du dt is minus gradient of the energy of u, and this is the equation, and you propagate, you solve this like a PDE, semi-implicit discretization. So the constraint that the norm of u, norm 2, it is equal to 1, is not satisfied by this tilde u, of course. And then you have to project this equation in order to have the norm equal to 1. That's why it's called a projected, a normalized gradient flow. Some remarks about this very this method introduced by Weizhu Bao, who will arrive this evening, and Cheng Du in 2004, has been used in so many papers. Two remarks about this method. The gradient flow that is at the origin of the method is lost at the discrete level because we discretized semi-implicitly, and the solution evolves from the manifold of the constraint. The manifold of the constraint, which is here, is the L2 sphere, right? So when you start from this state, you have a gradient, you have to go back to the L2 sphere. And sometimes, since it's a method which is inconditionally stable, this projection, it's quite rough. Okay, so what we can do about this? So the first idea that we had is to define a better gradient. So I will explain you what's the better gradient. So mathematically, you know that when you do a steepest descent method, you have to follow the minus gradient of the functional, which is the direction of the maximal variation, right? But this gradient is defined from the Ritz theorem, saying that the differential of the energy applied to direction h is written as the gradient scalar product, inner product, with the direction h. So your matrix or the direction of the descent depends much on the scalar product you use. Usually you use a L2 scalar product, but you can use more exotic ones like the H1, this is L2, H1 gradient, inner product, okay? So if you change the inner product, you change the direction of descent, and you change the way you measure your matrix, okay? And if this is the famous Sobolev gradient method, and if you look at the relationship between the H1 gradient, of course you can, by integration by parts, find very easily that you have this relation between the H1 an L2 gradient. And this is what? This is a very well-known operator that people in numerics know for a long, long time. It's what you call a preconditioner. Because if you go back to this equation, so instead of the gradient, you have I minus delta minus 1 in front. And people used with spectral methods will see that in spectral space, this is 1 over K2. Okay? And this will damp high frequencies more easily than in your original L2 method. So you have a smoother gradient and convergence. Generally, it's more rapid. So this is a nice way to put mathematically what was known for decades as preconditioners in numerical discretization of gradient flows. So the first idea we had, can we find a better gradient? And of course, the idea was to write the GP energy in a manner like in Ginzburg-Landau. So if you rewrite everything for the rotating system, well, I'm talking, like a gradient plus a term coming from the rotation, A, it's just an experp operator. You put into evidence what is called the effective trapping potential. So you have a system in rotation, and then from the trapping, original trapping, which is harmonic, you subtract the centrifugal force, of course. And this is something that physicists showed us, and then we say that, wow, this could be something interesting to look mathematically at, because in the Sobolev gradient, instead of the original gradient, we can take this convective gradient. Okay? So this is something, you remember Mark's talk, we had something gradient u plus something I times a velocity. And this is very similar, right? We have a convective gradient. In Ginzburg-Landau, here you have the magnetic potential, A. And this was nice because we can prove mathematically that the problem is well posed. Of course, there's also a Hilbert space. And we found that this kind of descent method with this A gradient converge faster. So this was the first point. And the second point is that instead of evolving the gradient, the gradient flow following directly the gradient and then projecting to be back on the manifold, it is possible to first project the gradient on the tangent space of the manifold and evolve your solution following this new direction. And this is intuitively better because you stay closer to the manifold. Instead of going from here to here, you can have a very small influence of a projection. And if you take this descent step reasonably small, maybe you don't need to reproject to go back to the manifold. And this is the projected gradient. And we can mathematically show that this is equivalent of what Ionut shown this morning, taking the Lagrange multiplier in the gradient flow. So this was nice, and we can do nicer methods, and it was a great pleasure to collaborate with Bartek Protas in this topic. Bartek came with a book, Optimization Algorithm on Matrix Manifolds by Apsel, Mahoney, and Spilker. And these guys are very used to solve PDEs on manifolds. And the descent method can be recasted on the spherical manifold. And what will be the idea? Instead of a constraint minimization, we can solve the unconstrained minimization, but on the sphere. This implies what? Two ingredients. The first one will be this projection, but this was equivalent to the normalization we've seen. If you have a gradient going there, you have to go back to the manifold. And in their terminology, this is called retraction. In the same time, you also need to transport vectors from one state to another, un minus 1 to un, and to stay tangent on the manifold. So this is an operator which is called transport of vectors on the manifold. If you use this, you can access to the steepest descent gradient method, but also to the conjugate gradient methods. And the classical, by example, Pollack-Ribier nonlinear conjugate gradient method can be easily recasted with these operators. So the only change is that you need to retract the advancement of your solution to go to the manifold, and all the vectors, gradient and also the conjugate gradient d, have to be transported using these transport operators. You recast the conjugate gradient. You see that mathematically it's a nice formula, but looks quite horrible when you look at the formula, but very easy to implement with FreeFEM, as we'll see very late. So with this, we can compute rotating condensates, and here you have rotating condensates with huge values of the nonlinear constant in order to obtain lattices with many, many vortices. So as I said, usually in experiments, there are 100 maximum vortices, but you can go up to 200 or 300 vortices in the condensate. And this will be a nice starting point for the simulating turbulence in BEC. As I said, once you have a nice converged stationary solution, you can do the Bogomolov-de Gennes linearization and look at the unstable modes. And we did this with Panos a few years ago, just to show you again that the linearized system for the two-component condensate looks quite involved. And if you want to code this with, I don't know, spectral methods or find a different methods, it's quite hard. But with FreeFEM, you'll see that it's very easy, and maybe tomorrow you'll see that it's very easy to define all the operators, to build the matrices, and to write code as you write equations on the blackboard. And we studied different states. Panos showed also some pictures of vortex, anti-dark vortex solitary waves, ring anti-dark ring solitary waves. And mesh adaptivity is one of the most interesting features of FreeFEM. You have here the vortex case and the ring case. So we can adapt the mesh and dynamically adapt the mesh at any iteration of the method in order to save time and to concentrate grid resolution where you have important gradients of the solution. And good news, as I said, numerical tools I will talk about are generally distributed as open source codes. So very soon, I hope that this paper will appear with the BDG toolbox with FreeFEM that will allow anyone to plug in a stationary state or to compute it with our toolbox and then to see the BDG modes and all the graphs of the eigenvalues I showed. So very briefly about FreeFEM. FreeFEM, it's a very popular software developed in mathematical community in France. It's a software developed by mathematicians and was designed to push mathematicians doing theory to test some numerical simulations. So the syntax is very close to mathematics. This is very interesting. It has a very powerful mesh generator. It has a lot of kind of finite elements, P1, linear, quadratic, P4 elements, and more exotic ones. You can have complex matrices, so for GP equation, it's very important. Mesh interpolation and additivity are very important, as you have seen in the previous picture. Every year we have a FreeFEM Days meeting in Paris. You're very welcome to come. It's a very friendly congress, and you can submit your problem. and there's a kind of brainstorming in the community to solve the problem. So many of the problems we developed and published then came from the suggestion from someone from industry or from other scientists saying, I have this problem, this PDE, how can you solve it? And maybe at the end of the 2-day meeting, we have already a solution. So to give you an idea how it works, and you'll see more tomorrow morning if you're interested, this is how to solve a Poisson equation in 5 lines. The first part, of course, is to define the mesh. As I said, the mesh generator is inside FreeFAM. So you have to define the border. Here's a circle. Of course, it's a parametric description, like in mathematics. Okay, so you can teach FreeFAM in parallel with calculus in your class if you want. You build the mesh from the circle, putting 100 segments on the circle, and you define a type which is a finite element space. So VH, as a mathematics, is the approximation of the Sobolev space used to define the finite element method, starting from the TH, and here's P1, linear finite elements, okay? And then you write the code. If you want to run the same code with P2, P3, P4, there's the only letter you have to change in your code, and all the rest will be done by FreeFAM. Then, the only mathematical ingredient you need is how to write a variational formulation or a weak formulation. What is this? You know that in finite elements, you don't solve the strong formulation of the PDE. You multiply with the test function, you integrate over the domain, and here you integrate by parts. So you end up with this equation, the integral over the domain of grad u grad v minus integral of fv equal to 0. And of course, the theory of the finite elements say that the v has to be in the same functional space as u, and this is the Galerkin finite element method. You took v successively any basis functions of the finite elements. So this is done very simply, because once you have the finite element space, you define your unknown and the test functions as a type, like integer or real in original code, uv. So these are finite element variables, okay? And then you write your Poisson formulation problem, Poisson of u and v, which is integral 2d of th, this is the integral 2d, of dxu dxv plus dyu dyv is exactly grad u grad v, okay? Minus integral of fv plus on the border one, u equal to 0, Dirichlet boundary conditions. And that's all. You just call the name of the problem and plot the solution. You see, you solve a very complicated problem in 3 lines. So Georges will show you more about that. So we used FreeFAM to compute many cases of BECs, and we publish also a toolbox with 2D and 3D methods for solving the GP equation, the stationary GP equation, and in particular these Sobolev gradients implemented in. So usually publish papers in computer physics communications, since we can publish the codes with the paper. And the codes are distributed from the CPC library. And this is quite convenient to have a serious paper and also to publish the codes. So these are some examples of the BECs simulated with this. And also, we were talking about vortex identification. We recently published a toolbox for vortex identification, also in CPC, with the codes distributed. So what is the idea? So the idea is simpler than that used by Giorgio and in the paper with Villois, is to use the power of finite elements to identify vortices very easily. So you have the P1 representation of the wave function, of course. A vortex, it's in 2D a point where both real and imaginary part of the wave function is 0. So we intersect the planes where the real and imaginary part are 0. We have the corresponding conditions to test if a vortex can cross a triangle or not, because we have triangular meshes. And then we can see if there's a circulation by approximating the Winding number with this very simple formula. And in this case, we can identify the point at which the vortex crosses the triangle. So this, since these are algorithms very well known in finite elements, are quite fast. So we tested on different cases. By example, this is a quantum turbulence simulation with the spectral code I'll show you after. And you see here the identification of vortices as usually with isosurfaces of low density. And this is what the post-processing gives. This is a computation on a grid, a modest grid of 256 cube. And it took on a laptop 12 minutes to have this, this field. And compared to a similar case in the paper by Villeroy et al., it seems that an equivalent case with around 600 vortices took 6 hours using MPI processes. But of course, their post-treatment was more precise and more appropriate to do Kelvin waves, etc. But if you want just to visualize the vortices and to calculate with a fair degree of approximation the vortex line length, this quite reliable post-treatment. Not necessarily. We have a graph. So we have loops. We can capture loops. We can capture individual vortices that go from one boundary to another. So
you get the curves, not only the position of the vortices, like points on the space.
yeah, we have the points. Yeah, we have make a catalog. Yeah. I didn't show the details because. But what is interesting is that this toolbox can be applied for BC. The situation in BC is more complicated because you have vortices on a Thomas Fermi parabolic, let's say, a background. Is not constant background as in helium. So to identify vortices, you have to remove the background, and then to identify vortices. It's more involved than in helium, in a GP equation in periodic boundary conditions. So this works quite well with numerical simulation, and here you have the image of a giant vortex, and also can be applied to experimental images. So we took from the paper by Coddington et al., one of the first papers with many, many vortices, and you see that even though the contrast is not perfect, the method can do a good job to identify vortices in experimental images. So the advantage of this toolbox, you can plug a numerical field or an experimental image or whatever you want with the wave function, and you can get the vortices.
So this was
Directly from the image from the paper. Okay. There's some filtering we did, of course. So another code that we're developing is the spectral code, of course. Everybody has spectral codes, and also we have spectral codes. And this code was developed in a former ANR project that I headed, 2013, 2017. This was exclusively with mathematicians, and there were many contributions on numerics and mathematical analysis of the GP equation, different types of GP equations. So you have the websites for all projects if you want to find papers and numerical codes. And this is a spectral code, as I said, with a stationary part, real-time part. So now we have relaxation scheme, all splitting schemes, also Crank-Nicholson scheme. And this is MPI OpenMP code, very well optimized by our engineers. And just to show you an image, good scalability, of course, and just to show you an image, a long time ago, in 2005, I simulated this, this giant vortex, just very, for people who do not know what's a giant vortex. So you take a condensate, you put it into rotation, and you see the Abrikosov lattice onset on the condensate. As I showed, if you take only harmonic potential, you have a limit of rotation, which is omega equal to 1, because the centrifugal force will balance the trapping. So in order to have higher rotation rates, you put an extra potential. So you have a potential R2 plus R4, and you can go to very, very high rotation rates. And at a certain moment, in the middle of the condensate, there's a depletion, and all the vortices in the middle will merge to make a hole. And this is the giant vortex. And the giant vortex is surrounded by individual vortices. And I simulated this in 2005, and for a grid of around 240 cube, each image took 2 weeks of CPU, and with the new code, it's less than one day. So it's very interesting to use parallel codes. Good. And also we simulated coupled condensate, fermionic and bosonic condensate, but I don't have time to show you the movies. And of course, the last part, but very shortly because Mark presented many things about this, is the okay, I told you that will be subliminal. Quantum turbulence. With this spectral code also, we published a paper recently in which we revisited some old simulation by Mark and Caroline Knorr. It's crazy how advanced they were in 1997 when they did the first simulation of the GP for quantum turbulence. Nobody cared at that time, but now it's a kind of rediscovery of this. So we revisited the GP quantum turbulence with this code, high performance code, to see how it works. So the idea of quantum turbulence simulations is how to set initial conditions. So we revisited the Taylor-Green vortices, the EBC flow, and also we invented new initial condition in order to have quantum turbulence, random phase field and random vortex rings. So this was a collaboration with Michikazu Kobayashi from Kyoto at that time, now in Kochi. And it was very interesting to do this simulation. And you have here just the illustration. And the idea was to evolve the code from a pure mathematical GP code to a more physical code. So we integrated all the ingredients to compute spectra, to compute structure functions, so on, in order to be able to discuss with physicists. I don't know if the movie will work. You have here the Taylor-Green degenerating in quantum turbulence, and again the vortex, and the ABC flow, and so on. We had a lot of fun. This is the an initial condition that deals only with the phase. So we manufacture the phase of the initial condition. So this is easier than the previous initial condition in which you take a model from classical fluids, you shift it to GP framework. You have to do some imaginary time to converge it. It's quite cumbersome. While here, you just set up the phase, and you can obtain a quantum turbulence that is equivalent to the previous one. Or you can set up, as in experiments, many vortex rings and get the associated turbulence. We also very briefly, Mr. Chairman, in the 3 minutes I left. 5 minutes, okay. So we also, since we had a spectral code for Navier-Stokes, a spectral code for the GP equation, we merged them to deal with the HVBK model, which is a very popular model to deal with quantum turbulence in helium. So in this model, which was briefly mentioned in previous talks, what we're doing, the superfluid does not anymore exist because the vorticity introduced by quantized vortices is just averaged. It's a coarse average of vorticity. So we have an omega S for the superfluid that will be used to derive a friction force appearing in the two Navier-Stokes type equations as a source term. And this is the coupling between the Navier-Stokes equation for the normal fluid, which is viscous, with the Euler equation, which will represent now the superfluid. So GP doesn't exist anymore here. The only presence of superfluid is due to this coupling force which is the friction force between the two fluids. And Luminita will present our results published in JFM about the high-order statistics and intermittency in this HVBK model, because she's an expert in classical fluids, and since HVBK, it's a kind of Navier-Stokes model, all the statistical tools used in CT can be applied, and nice transport equations for third-order moments were developed in this work. So next week, this will be presented. Now, Mark presented the coupling between Navier-Stokes and GP equations. So I just emphasize two ideas here, is that when we started to work on this coupling, we knew, of course, of the recent developments of coupling vortex filaments with Navier-Stokes, the paper in the groups in UK, France, and Japan. And our idea was a more, let's say, a mathematical and numerical challenge. So we have two different equations, how to couple them. Because we want to get rid of all the approximation of the vortex filaments. So no Biot-Savart-Laplace, no ad hoc models for reconnection. And also, we know that GP equation has all the ingredients to accurately reproduce the vortices in quantum flows. So we wanted to replace vortex filaments with GP equations. So we had to find the correct ingredients to do that. And of course, Mark's input was crucial in this part, because, as I said during the first part of my talk, the physical intuition is very important in this endeavor. So we managed to couple the two, and just to show you maybe the movie, because Mark showed it just this part. Just to see the difference, this is just GP equation with a vortex ring, and this is the coupled GP, two-way coupling of DGP and Navier-Stokes equation, with the formation of the two vortex rings in the normal fluid. So this, and again, this was the movie for the. You want to see it again? It's so nice. Now we are very happy with this, but as we discussed in length, our box is tiny, 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 but all phenomena that we observe are very similar to the phenomena observed in the simulation with vortex lines coupled with Navier-Stokes equations. So we hope that our exploration of this topic will give something interesting in the future. So it's time for conclusion. We develop many codes. This is our job. We're happy to collaborate with people from physics who need our tools and to learn something about physics and to teach them some mathematics and some numerical methods if it's necessary. Generally, people from physics say that they don't need this, but sometimes, you know, a kind of Sobolev gradient can be useful. We have many codes for the GP equation, a spectral HPC code. And the advantage of this code is that it's using only FFTW as external library. All the things inside are homemade, so we master everything. With FreeFEM, we have many toolboxes that are freely distributed. Don't hesitate to ask. To solve the stationary GP equation, to identify vortices, and also very soon for the BDG equation. So the idea is that you can use the solver, the finite element solver, to find a stationary state, or you can plug your solution coming from spectral, from whatever, finite difference method, or from experiments for the identification. This is very, very easy. And also we have HBVK solver, and now the coupled GP Navier-Stokes solver, also spectral. What I wanted to say is that the advantage of FreeFEM is that these codes are very easy to modify. So it allows one to focus on the model, physical model, and to not take care of all the numerical ingredients. So how to assemble the matrices, how to solve linear systems. Everything is inside. It's a kind of very evolved MATLAB for finite elements, very fast, and it's interfaced with many libraries, up-to-date libraries for linear algebra. The modes, it's, by example, BDG modes, we can use RPAC, we can use SLEP-C, and it's very easy. And also, for physicists, FreeFEM, it's a nice tool to do post-processing. If you have data, if you want to compute something like a PDE, it's very, in 3 lines, you can solve a PDE on your mesh, fitted with your experimental data. We use this for people from fluid mechanics doing PIV. So we imported PIV fields, and we did a lot of calculations, which are quite cumbersome to do with other methods. So I think, Mr. Chairman, thank you very much for your attention, and sorry for being so long.
Thank you, Ionut, for this interesting overview of all the stuff you've done for many years. So, any questions for Ionut?
So, Ionut, when you showed the U-shaped vortices, you said there was a race to understand somehow what is the right shape and so on. I'm wondering if you start, and you talked about a very prolate kind of condensate. I wonder if you start with a oblate or sort of nearly spherical condensate, then the vortex line would be essentially straight. And then as you go to more and more prolateness, the U should be sort of emerging because of curvature and so on. Yep. Did you ever study this as a bifurcation problem in the prolateness parameter somehow?
No, 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 it was not. But okay. You know that this is still a topic that we can work on it. But at that time, the experiments were on prolate condensate. And the idea is, if you rotate fast and fast, the line, the central line, will go up to the North Pole, but will never touch the North Pole. It will always be bended. And of course, there are explanations, physical and also mathematical, why it's doing that, because there's a problem minimization. And it's a very, very interesting problem, but was a lot of excitation around this, because the idea is, for experimentalists, was to obtain a single vortex line in the condensate, and it was quite work for doing this, but they did it.
So very nice, thank you very much. I have 2 questions. The first one is, how much level of detail can you actually capture in these modules? So you have these vortices that generate sound, or if you put some background noise to the system, can you still cope with that in a large size grid? And how much, what's the amplitude difference that you can capture small things?
Oh, you're talking about GP simulation for quantum turbulence. Yeah, I didn't have time, but yeah, this is from Mark's papers so many years ago. You have to carefully tune your cut wave number, and K psi has to be lower than 1 to have pertinent numerical simulation. And also, very important, you have to control the Mach number. The Mach number has to be low. In some simulation we've seen in literature, the Mach number is not so low, and the compressible energy could be quite important, yeah.
Thank you. And how easy is it to extend this to long-range interactions?
Oh, yeah, that's a question. There are many, many possible evolutions. Nothing is easy, but everything is possible. Thank you.
All right, so could you provide more details about the vortex identification algorithm? Is there some kind of variational problem involved?
No, the idea was to make something very simple. So, as Mark said, we have to find zeros of the psi function, right? So we use the P1 finite elements, very simple and very fast in finite element algorithms. All these algorithms are optimized. So if you have a piecewise linear function, of course, you want to find the intersection with the 0 plane here. and you have to intersect both the real and the imaginary part. So this translates in a very simple, because you have a continuous function, a very simple conditions about the variation of the real and imaginary part. And to find the intersection point, this is quite optimized in finite elements. It's a very, very fast algorithm. So this doesn't cost too much. And then to compute the winding number, you use an approximation of the circulation around the triangle. So the idea was to do something very, very basic. And this gives you the point where you have psi equals 0, real and imaginary part. So we didn't look at higher precision because the idea was to have something fast.
But can one guarantee that the zeros determined in this way actually form lines?
Oh, then, whoa, there's, of course, it's not only this. Then I didn't show you the picture. There's a whole algorithm to have a graph of the points and to follow lines. And you have loops. Okay, everything is arranged in the graph, right. And then we go up to the graph in order to identify lines.
Okay. Thank you.
Further questions to the coffee break.
Okay, thank you.